In September 1981, the Internet Protocol version 4 was formally codified in RFC 791. It remains the defining architectural achievement of the 20th century digital era. Operating at Layer 3 of the OSI model, IPv4 provides the logical addressing to identify hosts. It acts as the core shipping label for global data transit. It was designed for a catenet environment, an interconnected system of networks where data transmission requires no fixed logical circuits. Instead of dedicated pathways, IPv4 relies on connectionless datagrams. Every packet is treated as an independent entity, entirely unrelated to the one that came before it. The protocol is strictly limited in its scope. It guarantees the delivery of bits from a source to a destination, but delegates data reliability, flow control, and sequencing entirely to transport layer protocols like TCP. To understand modern network engineering, we have to look past surface-level configurations and deconstruct the mechanical limitations of this legacy 32-bit protocol, along with the subsequent patches required to keep it operational today. While network administrators configure systems using dotted decimal formats, routers do not read them. They process routing decisions exclusively through 32-bit binary logic. An IPv4 address is divided into 4 8-bit octets, with each octet representing a decimal value from 0 to 255. This matrix demonstrates positional notation logic. Each bit position corresponds to a power of 2, scaling from 128 to 1. To convert decimal 172 to binary, the system compares the value from left to right, turning required bits on, producing the binary equivalent 10101100. Early Internet design relied on a classful network model, dividing addresses into rigid classes A, B, and C based on their leading bits. This fixed boundary system resulted in massive address waste, as organizations were assigned blocks far larger than their actual host requirements. Subnetting provides the operational solution. In a default /24 mask, a boundary separates the network portion on the left from the host portion on the right. By moving this boundary, an administrator borrows 2 host bits, creating an isolated /26 subnetwork. New subnets are calculated by 2 to the power of n borrowed bits. Usable hosts use 2 to the power of h minus 2, removing the network and broadcast addresses. For our /26 mask, this yields 4 subnets, each supporting 62 usable hosts. Binary mathematics dictates the exact routing topology and network segmentation boundaries that keep organizational traffic isolated. This grid maps the IPv4 header block. Ranging from 20 to 60 bytes, it encapsulates every packet and acts as the protocol's operational engine, dictating routing, fragmentation, and lifespan. The first field is a 4-dit indicator identifying the protocol version as 4. Next to it, the Internet header length specifies the exact size of the header in 32-bit increments. The type of service field originally defined packet priority. Today, network engineers use this 8-bit block for differentiated services, allowing routers to prioritize time-sensitive traffic like voice-over IP. The time-to-live field is a self-destruct mechanism preventing infinite network loops. Every router decreases the TTL value by 1. If it drops to 0, the router destroys the packet and returns an ICMP time exceeded message to the source. Because the TTL field changes continuously during transit, the 16-bit header checksum must be mathematically recalculated at every single router hop to verify the header's integrity. When a datagram hits a network segment where the maximum transmission unit is smaller than the packet size, the router breaks the datagram into smaller fragments. The protocol controls fragmentation using flags. The more fragments flag signals additional pieces are arriving. Each fragment carries an identical identification number and a fragment offset field, specifying its exact position, providing the destination host a precise blueprint for reassembly. The strict formatting of these header fields allows datagrams to dynamically adapt to hardware constraints and survive transit across diverse network environments. The 32-bit architecture contains a hard mathematical limit, a total capacity of approximately 4.3 billion unique addresses. As consumer internet adoption accelerated in the mid-1990s, the engineering task force realized this pool would be insufficient to assign a unique IP to every global device. To delay address exhaustion, they published RFC 1918. This document reserved specific blocks of the IP space, like the 10 and 192.168 networks, for private, internal enterprise use. These addresses are not routable on the global internet. This private system functions due to Network Address Translation, or NAT, an essential technology installed on border firewalls and edge routers. NAT executes a process called masquerading. When an internal device sends a packet out, the NAT device physically rewrites the internal source IP header, replacing it with its own single public address. While effective for conservation, NAT violates the Internet's original end-to-end communication principle, creating complex routing hurdles for any protocol that requires incoming connections. When an internal host cannot reach a DHCP server to obtain an address at all, it initiates the IPPA fallback sequence. After broadcasting times out, the operating system self-assigns a non-routable link local address from the 169.254 block. NAT and private addressing prevented the complete exhaustion of the IPv4 pool, but they permanently fragmented a flat global network into isolated, overlapping private domains. IPv4 was designed for a trusting environment of academic researchers. As a result, routers make forwarding decisions based strictly on the destination header, implicitly trusting that the source IP is legitimate. Attackers exploit this logic through IP spoofing. By forging the source IP header, malicious actors can impersonate trusted systems and bypass network access control lists. When an attacker is on the same local subnet, they can execute non-blind spoofing to hijack active sessions. For external, large-scale attacks, they use blind spoofing, where they do not need to observe the return traffic. In an NTP amplification attack, the attacker sends a small spoofed data request to an unprotected server. Because the source IP is forged with the victim's address, the server sends a massive amplified response directly to the target, crushing their bandwidth. Organizations mitigate threats using strict edge defense filtering, rejecting impossible source addresses. Routers also use unicast reverse path forwarding. This cross-references an inbound packet source against the routing table. If the reverse route doesn't match the arrival interface, the router drops it. Because the IPv4 protocol lacks native cryptographic authentication, modern networks rely entirely on resource-intensive external validation rules to secure their perimeters. Mechanisms like NAT, rigid subnet boundaries, and edge filtering keep legacy networks functional, but they act as operational patches on an outdated architectural frame. The structural resolution is IPv6, codified in RFC 8200. It expands the primary address space from 32 bits to 128-bit capacity, yielding a virtually limitless supply of unique identifiers. This side-by-side diagram highlights the protocol optimizations. IPv6 replaces the complex variable-length IPv4 header with a streamlined fixed 40-byte block. To accelerate processing speeds, IPv6 eliminates the checksum requirement entirely, assuming modern transport layers handle error validation. It also removes in-transit fragmentation. Routers no longer split oversized packets. That operational burden is placed solely on the sending node. IPv6 integrates IP6 as a mandatory feature, providing native end-to-end encryption and cryptographic integrity to prevent address spoofing. As global networks transition to IPv6, the engineered constraints, binary logic, and adaptability of IPv4 remain the bedrock of modern network operations.